All right, let's continue here. We talked about bundle adjustment, and we talked about the, the famous gradient descent or steepest descent algorithm, an algorithm that steps down into the minimum. And as you can see in these visual examples, it's not a very, technically deep idea. You just iteratively step down to the minimum. And if you have a convex energy, meaning you only have, sorry, here we are back again. You only have one minimum, then it finds that minimum. In most loss functions, though, your energies are not convex, which means you may have local minima, and then you will typically end up in some local minimum by this procedure. And this is, for example, the case when you train a neural network. Typically, the loss functions are not convex, and so all you can expect is a local minimum. Why these local minima that you find when training a network are still good, this is, to my knowledge, still more or less a mystery. There is a lot of research that went into it, but typically, once you have a non-convex problem, there isn't so much you can prove about optimality of solutions. But it's kind of the workhorse for a lot of optimization approaches. Here's this idea, this iterative approach. You step to a local minimum. What we're going to do now is we're going to look at problems that are a little bit more structured, not just a random loss function, but a loss function of a particular structure. And in these cases, there are more efficient algorithms to optimize. Let's take one example. It's a very simple one. It's linear least squares estimation. So the idea, you all know this, is that you have a set of points and you try to fit a line through it, right? For example, if you can have a linear dependency between an input, an input vector bi and an output vector ai, and the linear dependency is captured by ai being bi transpose x with some vector x. So this is and then you have a Gaussian, some noise that is added to it, this eta I, and typically you would assume some noise such as zero mean Gaussian noise. So sampled from a Gaussian distribution with zero mean and some covariance matrix sigma. And for simplicity, let's assume this covariance matrix is diagonal, so it's the identity times the variance sigma squared on the diagonal. What you can do then is you can do what's called maximum likelihood estimation to determine the unknown parameter vector x that models the mapping between input b and output a, right? And if you apply maximum likelihood, say find the most likely x given a lot of sample data ai bi, and then you can show this leads to an ordinary least squares problem. How do you show it? Well, you set up the probability distribution, you maximize it, and then you can equivalently minimize the negative logarithm. And if you apply the negative log to a Gaussian distribution, you end up with a quadratic loss. It's a fairly standard procedure. And so you have this loss function. If you will, you can write it in this way, a minus bx transpose times a minus bx, where b is the matrix containing the vectors bi. This idea is called linear least squares estimation. It was introduced by Legendre in 1805 and kind of independently or in parallel by Gauss around 1800 as well. And in fact, this is an important development. This is where the Gaussian distribution emerged. In fact, it didn't fall from the sky. The question that Gauss asked is, if you do least squares estimation, and you want to fit a model, what is this kind of what noise distribution do you need such that the maximum likelihood estimator ends up being the mean? Right? In which case, in which noise distribution do you get the arithmetic mean? Because typically when you have, this amounts to computing the mean. And the question is, when do you expect to find the mean, under which distribution? And this is where he found the normal distribution, how he called it. Obviously, he didn't call it Gaussian distribution. And so this is how the normal distribution was invented. It is the distribution that, in the maximum likelihood estimation case, leads to the arithmetic mean. And the nice thing is about this whole approach is that this is a quadratic loss function, and so it's very easy to minimize, right? If you want to minimize this, even in the more general case, when you have Gaussian noise but zero mean, but some random covariance matrix sigma, then you get the generalized least squares problem where you minimize this expression here. And you can see this is exactly the exponent of a Gaussian distribution. Once you apply the negative logarithm, you get this thing down as the loss function. So this is a quadratic loss function. Once the covariance, the inverse covariance matrix, the positive definite inverse covariance matrix, and the closed form solution is you minimize this. How do you minimize it? It's a quadratic function. You set the derivative to 0. So the derivative with respect to the unknowns, you set it to 0, and you end up with this expression for x. If there is no correlation among the observed variances, then the covariance matrix is diagonal. So this would be the case that we had here with a diagonal covariance matrix. Then typically this problem is called weighted least squares. Why am I telling you this? Well, I should be honest, I was kind of confused myself a few years back about all the different terminologies that people have. There's least squares, there's weighted least squares, there's generalized least squares, there's nonlinear least squares, there's iteratively reweighted least squares. At some point you get completely confused what is what, and so I wrote it down here on the slides. So the least squares is this one, ordinary least squares it's called. Then with the covariance matrix it's called generalized least squares, and if that covariance matrix is diagonal, where the diagonal elements are of the inverse covariance matrix here are sigma I to the minus 2, and these are the weights here, then it's called a weighted least squares problem. You can obviously consider the case that the covariance matrix of your noise is unknown, and you try to estimate it along with the parameters of everything else. Then there is an iterative estimation. It's called feasible generalized least squares, and in the diagonal case it's called iteratively reweighted least squares. So what does that mean? It means I minimize this loss function, I keep the weights fixed, and then I update the weights iteratively. This is then called iteratively reweighted least squares, a fairly powerful algorithm that often converges very fast. So here's how it works. So we have this loss function, and the idea now is that we have a least squares problem with weights, but the key thing is that these weights actually depend on the solution. And there are many interesting problems that can be cast into this form. Maybe I'll mention one of them. Let me get one of the boards down. Well, that's going to take a while. I think these boards must be from the 19th century. I don't know whether Gauss put them up himself. All right, there's some space. So one of the loss functions that you want to minimize is a sum where you have the norm, just the norm, so not the norm squared, but just the norm, say ai minus f of xi. And the way you can do that is you can write it as a weighted least squares problem where you do wi and then ai minus f of xi. F of x, squared, and then the weights, these weights, they depend on x in the way that with wi of x is just given by 1 over this expression, 1 over ai minus f of x. Right, and you see if you insert that weight in here, you get exactly this expression. And so this is called robust least squares estimation because it's more robust because you don't have a quadratic loss but just the norm. And you can write it as a weighted least squares problem. And this is often how you optimize that you minimize this because it's, apart from the weights, it's quadratic. And then you keep the weights fixed and then update the weights accordingly. So first estimate the solution in x, then update the weights, and then re-estimate the solution. That's why it's called iteratively reweighted least squares. So this is one example problem that you can tackle with iteratively reweighted least squares. And the idea is you see it here, we get a solution in x where for time iteration t plus 1, where we keep the weights as a function of the solution at time t. And then it's a quadratic loss function, so it's easy to minimize. And so in each subproblem we solve this problem. So whether it's quadratic depends obviously on the residual f of x, fi of x. Sorry, there should be an I missed an I. So this is how you can solve it iteratively. Whether it's convex depends on the residual, but if f is linear in x, then this whole thing here ends up being quadratic, in which case we can solve it easily. What's important though is to keep in mind that once you have a weighted least squares problem and the weights depend on x, strictly speaking, the overall problem is generally no longer convex. And so this approach tends to work well in practice. For example, for this robust estimation approaches, it works quite well, but there is no guarantee that it will find the global optimum. This is very common. As soon as you have problems that are not convex, there is a whole zoo of algorithms that you can throw at it. Even if they work in practice, it doesn't mean they give you guaranteed optimal solutions. And sometimes I see that people confuse that. Even in the neural network age, they throw gradient descent on a non-convex problem, and then they say our solution is the optimum. Well, it's a local optimum, but it's not typically the global optimum. In addition, and this is probably the most general form of least squares estimation, we have something that's called nonlinear least squares estimation. That's kind of the generalization of all of it, where you have a least squares problem of the type that you have residuals squared, summed up, and then you have some residual that depends on your unknowns in some form. Typically some fitting problem where you have a function that maps an input bi to an output ai with an unknown parameter vector that models that functional dependency. And that can be linear, but it can be quadratic, and it can be anything, and typically you don't know what it is. But it's some parametric function parameterized in a parameter vector x that maps from input to output. And ideally input and the input should map to the output in the sense that the discrepancy, the quadratic discrepancy, is minimized. And as we saw, bundle adjustment is exactly that. In bundle adjustment, I have points in 3D, I project them into image, and this is happening by this residual. I'm measuring the discrepancy between the observed point and the projected point. And then I minimize the quadratic discrepancy for all the points that I observe here. So I is a summation over all points projected into all sorts of images. And so you can check for yourself, but the bundle adjustment, where was it? Here is exactly in this, where is the best formulation? This one maybe is exactly in this form, right? We have a residual, we have the observed point, and this is the mapping of the projected, of the point, the projection into, of point xj into image I. And we minimize this discrepancy, and so it's exactly in this form that we call nonlinear least squares estimation. Important to note, generally this is not convex, even if at the first glance this looks quadratic. Depending on how it actually depends on x in the residual, it may be non-convex. If f is linear, then we have a quadratic loss function, but in general f will not be linear as a function of x, and then this will not be convex. But what's nice is you can write down formally the optimality condition for this. Right? How do you do that? Well, you set the derivative of this thing with respect to x, you set it to 0, right? If you do that, then you have to apply the chain rule, right? So you get 2 times ri times dri by dxj equals 0 for all j. So this is the derivative of this residual with respect to xj for all the different unknowns xj. This is nice, so that's the optimality condition. This equation is what I need to solve. Unfortunately, you can typically not solve this directly with respect to xj. And so you revert to iterative algorithms to compute solutions. And you can apply a gradient descent, obviously, to this, but you can apply more sophisticated algorithms, and we'll talk about some, including the Newton method, the Gauss-Newton, and the Levenberg-Marquardt algorithm. And so here they are. The Newton method is a very general optimization method, and here as well, these ideas are not terribly profound. I remember when I first started thinking about how can you find the minimum of a loss function, you have a loss function like so, and then you read about gradient descent and how you kind of step down into the valley, and then you start thinking, well, if I can fit the first derivative here, that tells me where does it go down, is it not possible to fit the second derivative as well, right? Once you start computing derivatives, why don't you compute the second derivative and thereby fit a parabola to this whole problem? Why is that useful? Well, for a parabola, I know how to find the minimum. There's a closed form solution to find this position where the parabola has its minimum. Right? So what you can do is fit a parabola, step to the minimum, and then here fit another parabola and step to that minimum. It's something, for example, I remember when I was studying, I thought of this would be the right idea to do it, because then you don't need step sizes that you need in gradient descent. You fit the parabola every time you keep going. And then much later I read up about it and found out this is a known procedure, and it's called the Newton method. I mean, it's so obvious that even hundreds of years ago people came up with it. Not very profound. And how does that work? Well, you all know how to fit a parabola. It's called a Taylor approximation, right? So you take your loss function and you approximate this loss function. Let's say E is the loss. You approximate it, iteratively. So at iteration t, I fit it. I have some point xt. So that would be my initial point xt here, right? And I fit the first and second derivative. The first derivative at xt I call g. The second derivative is the Hessian matrix I call h. And then this is a quadratic fit. Minor comment, by the way, I mentioned bundle adjustment was largely developed at TU Munich. Hesse from the Hessian matrix, guess where he was a professor? At TU Munich, right? You may not have known that, yeah. But so a lot of the foundations for all of the things we do, go back to people who were here. So this is the second derivative, and this is the quadratic fit, first order linear term, second order quadratic term. So this is this orange parabola, right? And now we say find the minimum of that parabola. How do we find a minimum? We take this quadratic approximation and we set the derivative to 0. Meaning we find the place where this is horizontal, the derivative of this quadratic. If we do that for this approximation, I should say this is not exactly dE by dx, but it's the derivative of this approximation with respect to x, right? And whereas x, there's a linear term, so we get the g. And then in the quadratic term, it's just h times x minus xt. Now we set this to 0, and surprise, surprise, it's a linear equation. It was built that way, right? It's a quadratic fit. Once you take the derivative, you get a linear equation system that you can solve, and the solution is just given by xt minus h inverse times g, right? If I solve this with respect to x, I find the next update here. This is x. That's the next iterate, and so I set the next iterate, I call it xt plus 1, to the solution of this equation. So this would be my xt plus 1 would then be here. And as you can see in this drawing, that's why I drew it this way, it is fairly close to the minimum. Obviously this is a technique that's not always going to work, right? If I start at a very bad point, let's say here, and I fit a parabola, and the loss function looks like that, then the parabolic fit, it will look like that. It doesn't even have a minimum, right? So you got to be in the right regime where things are actually, bending inwards, where you have a positive, definite Hessian matrix to fit the meaningful parabola. And this is typical for the Newton method. It tends to work really well and is very fast, provided that first of all you can actually compute the second derivative, right? That's something you need. And secondly, once you're in the basin of attraction in this kind of concave setting, convex setting, then it will typically converge very fast. What's interesting to note is if you look at the update equation, it is very similar to the gradient descent When I have people in exams, I often ask them if they know the update for the Newton method, and surprisingly many people don't know. It's not so different from gradient descent, right? What do I do in gradient descent? I take epsilon times the gradient, then minus epsilon times the gradient. Here we have almost the same, except the step size in the gradient descent is replaced by the inverse of the Hessian matrix. And that's where it's adaptive, meaning if it's a very curved part, it will take a smaller update step, and if it's a very flat part, it will take a larger update step, which kind of is meaningful, I would say. Typically, you can choose a more conservative step size if you're a little bit hesitant whether the inverse Hessian is a good estimate for the step size. You can add a gamma between 0 and 1 to have a little bit more conservative update steps. When applicable, that means when you can compute second derivatives and when the Hessian is positive definite, then second order methods are typically faster than first order methods, at least, and this is important, when measured in the number of iterations that I need. And this is unfortunately a discrepancy here, right? Why? Because in every iteration I have to compute the Hessian and I have to invert the Hessian. Computing this and inverting it can be time consuming. So even if you need fewer iterations in a Newton method, it doesn't mean in terms of clock time you will actually be faster. Right? Because if every iteration takes a lot of time to compute, then you're wasting time there. And so there is a trade-off that you end up finding between, optimizing iteration counts and optimizing actual clock time. And partly due to this discrepancy, there are two communities in this optimization world. The first order people and the second order people. And the second order people will always say, we are faster when measured in iteration numbers. And the first order people will then respond, yeah, but in terms of actual clock time, you're not, right? And then even more so, which approach is more suitable, first order, second order method, kind of depends on the hardware that you have to implement things. For example, if you run things on a GPU, something that's become popular in the deep learning world, but that's been around for, we started running algorithms on GPUs around 2004, so 20 years ago, on NVIDIA GPUs, incidentally. And when we did so, we showed in many papers that you can dramatically accelerate compute once you run things on GPUs. But there is a trade-off. There are certain things that are not so easy to parallelize. For example, matrix inversion, right? So if you, in every iteration, you have to compute and invert the Hessian matrix, this may be something that doesn't port well to the GPU. In which case you don't profit from the massive acceleration that the GPU gives you. Meaning even if the second order method is faster in clock time on the CPU, it may not be faster on the GPU. And so this makes the whole story of what is better really complicated. And while in principle second order methods have advantages, it's tricky to get them working. For example, to my knowledge, one of the biggest challenges nowadays in optimization is to optimize neural networks. And to date, people don't seem to use second-order methods. And we tried, many others tried. There is a challenge to make them work. One aspect is when your problems get really big, the Hessian matrix gets massive, right? And then you cannot really invert it, you cannot store it, you cannot invert it, so you have to come up with more clever methods. And then typically you can expect that the Hessian matrix will generally not be positive definite. There are then ways around it. There are so-called quasi-Newton methods, and these basically approximate the real Hessian by a matrix that is similar but positive definite. So basically saying whatever negative eigenvalues it has, you just clamp them to 0, and then you hope that this will do the trick. And that's one way of doing it. Or you can invert the Hessian and then approximate that with a positive definite matrix. So there is tricks, and these are called quasi-Newton methods, and they can be shown to work. There are also methods that deal with non-differentiable problems. There are so-called semi-smooth Newton methods. So there's a whole zoo of techniques to make Newton methods work in a bigger range of problems. And hopefully one day someone will come up with a solution for training neural networks with second-order methods, and that might help reduce the carbon footprint that we leave. Here's a variant of the Newton method that is really popular, and that is the power horse of all bundle adjustment. It's a technique called the Gauss-Newton algorithm, and as you can see, it was named by two of the most influential scientists in history. It solves nonlinear least squares problems of this form, like we discussed. And the idea is the following. It can be derived as an approximation to the Newton method, right? So we take this nonlinear least squares and we run a Newton method on it. What does that mean? It means we compute the first derivative of this loss function. This is it. Chain rule, right? The gradient. So Ri times dRi by dxj. We saw that before. And then we have to, in the Newton method here, in the update, we need the Hessian matrix. So we compute the Hessian matrix, means we take the derivative of the derivative. So that would be the second derivative matrix. So we take Gj and take the derivative with respect to xk. And so hjk, the component of the Hessian matrix xjk, is the derivative with respect to j, and then derived again with respect to k. If you do that here, you have to do the product rule as well, right? There are two terms. There is residual and its derivative. We take the derivative with respect to xk, so we get a first term, which is dri by dxj and times dri by dxk. That would be keeping this term fixed and taking the derivative of that term. And then we have another term which is keeping this term fixed, ri, and then taking the derivative of this one with respect to xk. So we have a second order derivative of the residual. And now comes the key approximation of the Gauss-Newton method. It takes this Hessian matrix with these components and says, let's just ignore the second order term, right? With respect to the residual, we have here the first order derivatives, a product of two first order derivatives, and here a term involving a second order derivative. And that's the term we're just gonna kick out, just ignore, and approximate it with 0. It's a bit of a brute approximation, and we can come back to whether that's a good approximation or not. But what we end up getting then is an approximation of the Hessian matrix, which involves, if you call this the Jacobian of the residual, Jij is the derivative of residual Ri with respect to xj, then this is just J times J. J transpose J, basically. And this is the approximation of the Hessian matrix. So if you call J the matrix of, this is called the Jacobian matrix, is the matrix involving the derivatives of all the residuals with respect to all the unknowns, then the approximation is that the Hessian matrix is 2 times J transpose J. And then, if you look at what was the gradient of our loss, this was just, you see it here, this is J transpose, this is R. So J transpose R was the gradient of our loss function. And so the update in the Gauss-Newton algorithm is take the old iterate and the update plus the update delta, and delta is J transpose J, so our Hessian approximation here, inverse times J transpose R. The factors 2, as you can see, they cancel here. So this is the update rule for what's called the Gauss-Newton algorithm, and it is an approximation to the Newton algorithm. But what's really beautiful is, in principle, it's based on a second-order optimizer, but with respect to the residual that enters my least squares problem, it only involves first-order derivatives. And that makes it very powerful and very practical, because you have a residual and all you need to compute is the first derivative. Then you take that first derivative here of your residual and you construct this update. All it takes is the residual and the first order derivative of it. And that gives you the Gauss-Newton method. And the nice thing about the Gauss-Newton method is it has a convergence behavior much like a second order method, even though it only requires first order derivatives, because it is based on an approximation of the second order derivative matrix. And the beauty of this is twofold. First of all, I only need to compute first order derivatives, not second order derivatives, because I ignored the second order derivatives in the approximation. The second beautiful thing is this matrix J transpose J by construction is positive definite. How do you see that? Well, if you take J transpose J, the approximation of the Hessian matrix is positive definite in the sense that if I do X transpose this times X, then this is the same as Jx norm squared, and that obviously is always non-negative, right? So you can see this Hessian matrix that we approximate with J transpose J is by construction positive definite, or semi-definite at least. When is the approximation good? You know, we kicked out a term. That's a bit of a drastic move, right? When can we expect this to work? Well, we have two terms that make up the Hessian, the components of the Hessian matrix, the first order derivatives and the second order derivative term. And clearly the approximation is good if this term is much smaller than that term. And so this is basically the regime in which the Hessian approximation is valid. When does that happen? Well, it happens once the residuum is small, right? Once we're near the minimum, we expect the residuum should get 0 at that point. That's how everything is constructed. So once you're near the minimum, Ri will be near 0, in which case this thing should be a good approximation. Or if the residuum is close to linear, right? If Ri is linear, then the derivative is constant and the second derivative will be 0. So as soon as you have something where the residual is nearly linear in x, then the second derivative will be approximately 0. And then you can expect this approximation will be good. So either once you're close to convergence or once you have an essentially approximately linear problem, the residuum being linear, then this will work well. Now, whether these conditions are fulfilled is another matter, but in practice, this Gauss-Newton algorithm works well. But you see already that you have an interest in making a nonlinear least squares optimization problem where the residual should ideally be approximately linear. And the more linear Ri is in X, the better this algorithm will work, the faster it will converge. Maybe a few more things here. There is an extension of the Gauss-Newton algorithm that is called the Levenberg-Marquardt algorithm, based on two researchers by the names of Levenberg in 1944 and then later Marquardt in 1963. And they suggested something that can be seen as a hybrid between a Gauss-Newton algorithm and a gradient descent. And this comes from, if you look at the Newton update, here it is again with the inverse Hessian as a weighting of the gradient vector. You can actually create hybrids of Newton and gradient descent. As I mentioned, gradient descent and Newton update are practically the same. One you have a step size and one you have the inverse Hessian, right? Well, you can combine them. You can have a step size lambda and the Hessian, and there's different ways to write it, but this is one way where you basically take H plus lambda identity and then invert it. So you have, and you can see, for lambda equals 0, you get back the Newton method. And for very large lambda, this term will dominate, and then you have something that is very much a gradient descent, because then you just have a scalar term dominated by this expression here times g. And so this is called a damped Newton method, and it's in some sense a hybrid between Newton and gradient descent. Depending on how you choose lambda, you get either more Newton if you set lambda to 0 or close to 0, or you get more gradient descent if you take a large lambda. Why would you ever do that? Well, for example, if you have a loss function that is, like so, then in this regime you don't want to compute the second derivative matrix because it's not convex. You're in an area where things are very concave, right? Your Hessian will not be positive definitive. The parabola fit will open to the bottom and it's kind of unbounded below, right? So what you want to do here is you want to start with a gradient descent that gets you down the hill, and once you're in a regime where the curvature changes, right, then you want to switch to a Newton method. And typically once you get closer to the minimum, to this basin of attraction, that's where you want to move to a Newton method. How can you do that? Well, you can take a damped Newton method, start with a very large lambda, meaning do gradient descent, and at some point reduce the lambda and thereby switch to a Newton method. And you can kind of continuously change from a gradient descent dominated approach to a Newton type method. And this is some of the things you can do with this damped Newton methods, right? And now obviously you can do the same damping in the Gauss-Newton approximation, right? Here, how does that work? You have the Hessian that's approximated by J transpose J, like we saw, and then you add a little bit of gradient descent into it with this lambda weighted identity. And this is called the Levenberg algorithm, works really well. And then you can do, and Marquardt spent a lot of time looking at this algorithm and its variants to optimize loss functions. And what he cared about were often loss functions that were highly anisotropic, where you had very thin valleys, and then you find you want to have a more adaptive approach where the damping is more component-wise. And so rather than adding lambda times the identity, you add lambda times a diagonal matrix that on the diagonal has J transpose J. So you take your Hessian approximation, you take the diagonal elements, and you do something that is kind of more adaptive. So depending on what the size of J transpose J is on the respective diagonal elements, you use something that is kind of where the lambda is kind of in proportion to whatever is already there on the diagonal. And so that makes it more adaptive. And so what he found is that makes the convergence faster, especially when you have very anisotropic loss functions. Often in optimization, if you have a loss function that is isotropic, then life is easy. But if you have such elongated structures, I mentioned it last time, then already the gradient descent will, zigzag forever. And so there needs to be adapted versions, and this is one. As I mentioned, let's say in the neural network world, there is also similar adaptations of the gradient descent algorithm. For example, some people may know that neural networks are optimized by an algorithm called ADAM, and this is an adaptive momentum algorithm. So it's kind of in spirit related ideas of how to adapt gradient descent type algorithms to deal with anisotropic loss functions. All right, this brings me, I don't know if I should mention this, there's a lot of math. So that gets us back to the bundle adjustment, and what we're going to do in the next session is how to discuss how to apply Gauss-Newton and similar types of iterative algorithms to solve the bundle adjustment problem. I should say next week is one of the biggest computer vision conferences. In fact, the biggest computer vision conference is a conference called CVPR. It's not just the biggest computer vision conference, but it's actually the biggest conference in the world. In terms of impact factor, there is no conference bigger than that across all disciplines. So it's the flagship conference in the fields of computer vision and AI. It's in the US, in Nashville, and I will be there to present a lot of research that we're doing and also to follow up on the latest trends and developments in the community. And so unfortunately I won't be here next week, and so I would ask you to revert to, like last time, we'll upload videos that you can watch and they will cover this material. I know it's always, especially for the people sitting here, you'd prefer live. I'll be back live the week after, right after CVPR, and I'm looking forward to actually seeing all of you back here again then. Thank you.